of this conference. And the first speaker today is Professor Junggi Yoon from APCTP, and he's going to talk about the negative central charge and unitarity. Okay, thank you. Please.
Thank you for introduction. I would like to thank I'm organizer, but anyway, I would like to thank Sang-jin and Keun-young to give an opportunity to present this work. Let me start with unitarity. Unitarity is a very important postulation in physics, especially in string or half PH. We constrain a lot of theory by using the unitarity. But in practice, we often use this unitarity with very different various meanings. Like, for example, we usually in the quantum mechanics, like a lecture, we say unitary. This unitarity means unitary time evolution. Or sometimes people say it's if you find the negative norm state, then you say it's non-unitary. Or sometimes if you find some instability, then you also say sometimes you say it's non-unitary. But it looks like they are different, but often they are close to each other, related to each other. So, however, now there is also non-unitary physics. So this non-unitary physics was people are interested because of the open quantum system. So everywhere there are in our life it's an open system. So experiment or universe. Of course, whole universe is maybe I believe unitarity, but a closed system maybe or not. But what we observe is like some certain. What we can observe would be some open system. And because of the coupling to the environment in the open quantum system, it is inevitably non-unitary. Actually, I'm not 100% sure about this statement, but often it's true. And the non-unitary time evolution, or almost it's the same to this non-Hermitian Hamiltonian. Now it's very important. Now, as I said, many people are working on this subject. And there are many ways to judge whether its system is unitary or not. Like there is also S-matrix, there are many like theorem people study, and also this cutting rule is one of the way to judge the theory is unitary or not. In Shape-T 2, we have a very nice quantity called the central charge. And this charge can judge whether system is unitary or non-unitary. So this like in yellow book, you can easily see that CFT2 with negative central charge is non-unitary. Actually, I'm not sure the other, like CFT2 with positive central charge is unitary or not. That I'm not 100% sure, but I think that is usually okay. So in this talk, I will answer to this question: does the negative central charge always imply non-unitarity? And actually, it's also involved with this question. Is the hermiticity of the Hamiltonian always clear? Actually, the origin of this my talk is actually more related to this question. So let's see. So outline is I will focus on this quantum mechanical toy model. And this is very easy. Like I think undergraduate students also understand it. And the next one is symplectic fermion. That also a little bit require the Shapley-2, but it's really basic. So let's go. So quantum mechanical toy model. So this is a work based on the Kyung-sun Lee here. He is the PhD in the GIST, and he will graduate in next year. He's really worked nicely in this project. And also PhD Lee from PIAS. And we published this paper in the last year, but somehow this model is hidden in the appendix. I found it very interesting, but no one is interesting because I found yesterday I found that there are typo, but no one pointed out. So that means no one read it, but I think it's very, very important. So in that paper, you don't have to worry about the TT body formation, but in that paper, our motivation is TT body formation. We consider some kind of irrelevant information from the IR to UV, following some spatial flow equation. And then there are some two results, depending on the definition of the energy moment tensor. This is some, and you don't have to worry about some detail. But the other one has this kind of quadratic in the time derivative. So here you have a dot, it's quadratic in the side dot. So this is the kind of fermion doubling problem. It's not the doubling problem in this lattice one, but it's you will see soon. So this was our motivation. We trying to understand this system so that we study this kind of very simple quantum mechanics. So you just now forget about the TT body formation. You can just focus on this one. So this is kind of deformation of the free fermion. This is usual one-dimensional free fermion quantum mechanics with this deformation. And this deformation, as you see, it's very similar to this kinetic term of boson. And now this is really basic. You just calculate now I will consider this canonical quantization, which means that I first calculate this conjugate momentum by derivative of the Lagrangian with respect to theta. Then you can obtain this one and this one. So usually in fermion, you don't have this term. That means this becomes the constraint, and then this constraint reduce the degree of freedom. So in the end, you only have a psi and psi bar in your phase space in the usual fermion. But in this system, this is really similar to this scalar field or boson, so that you can express psi dot in terms of other phase space variable. So that means there is no constraint. And like a scalar field, now this four field now become the phase space variable. So that means it's doubling, but it's not related to doubling in the lattice. So now we will quantize the theory by using this oscillator. So there you can this theta is for now you can think of some parameter. Actually, it's related to the Bogoliubov transformation, but you can imagine that you can expand this pi and psi. This is just can think as like some kind of canonical transformation or some other one parameter family of the linear transformation. Then this usual canonical anti-commutation relation becomes this oscillator algebra. And this actually the most important part is this one. The usual fermion oscillator has 1 on the right-hand side, but this C fermion, it has -1. So this is kind of inevitable. You're trying to do this kind of transformation, you cannot observe this one. Like a scalar, like a later next part I will explain, but this usually boson, you can exchange the C and the creation and the annihilation operator. Then like a roll over the creation and annihilation operator, you can flip the sign because it's anti-commutation relation, but this is for anti-commutation relation, so that such kind of trick does not work. So this is essentially some important and physical. And then we can express Hamiltonian in terms of the B and C. Then let me ask whether this Hamiltonian is Hermitian or not. So you can, this theta and m and lambda are all real variables. So you might say that it's Hermitian. But let's see. So if you have 2 students, you can give them homework. So for Bart, I will give this Hamiltonian. And as usual, you can ask them what is the energy spectrum. So what they can do is that they can evaluate this kind of the matrix representation by using the Fock space, and then you obtain the matrix, numerical matrix, and then you just diagonalize. That's all. This is very simple, 4x4 matrix. Mathematica easily do. Usually Mathematica is much better than the PhD. So yeah, then can you get? For Lisa, she must be smarter than Bart or senior, so that I can give this Lagrangian and ask them to calculate the partition function. Because this is quantum mechanics, it's easy to evaluate this kind of this fermion the path integral, and you can obtain partition function. It's very easy. Actually, because it's quadratic, you can calculate everything. Then next day, Bart will give bring this result. And Lisa will give give you this result. And the result is different. Here, Bart results. These are energies are real for every mn lambda, for real mn lambda. On the other hand, if you see the Lisa's result, it could be complex for some mn lambda. So this is something strange. So if you answer to this question, like if you answer yes for this question, like if you think this is a Hermitian, then you think that the result of the Bart is correct because the Hermitian Hamiltonian gives the real energy. But let's consider the system a little bit more. There is a problem. Because here, this C and C dagger has this kind of anti-commutation relation. And you can calculate the norm of this state. And then this is simple. You just calculate it. And then because of this -1, you obtain this one. And then norm of the ground state is opposite to the norm of the first excited state. That means either vacuum or this state has negative norm. Actually, this looks like a very similar to the Ostrogradski instability for higher derivative theory, where here this is not the extremely higher derivative, but compared to the free fermion, it has a higher derivative. So this instability, you can also see some same structure, but I omit that story. So you might think this model is pathological. So why we have to consider it? Maybe it's too early to conclude that because there is resolution of negative norm. So one can define this kind of J operator. Yeah. You can however you can use the microphone for the negative. This is just a calculation. No, it's not pushy. It's a canonical quantization. Probably. Tangin asked why this you are using this anti-commutation relation minus, but it's not my choice. Just if you canonically quantize it, what you obtain is this one.
But that is just a consequence. I think that gives you the norm of the
so
I mean the state created by C is negative. Therefore, usually people don't do that. But here you have some reason to do that. And
no,
I want to.
This is not what I do. This is just if you just using the canonical quantization.
Quantization. What do you mean?
Over this you agree that this is canonical quantization because this is consistent with this Hermitian. So this -y, and then
she was defined. I'm sorry. I'm sorry. So I see. You start from psi and pi.
And then this is just a linear transformation. You can find
I'm sorry. So that means that this theory contains the ghost, right?
But it's too early to say that. Actually, I expressed.
But I think to me, it's obvious from the beginning.
No, it's not obvious. I will explain. So at first time, I thought it's strange, and historically, also some people relate to the ghost, but it's interesting. So that's why I explain. So yeah, I agree that we all of us. If you see this kind of, even without the analyze, we expect that this theory has ghost and some problem because you higher derivative, but something is non-trivial. That's what point of my talk. So there is just this kind, you can define J operator, which is usually very similar to this number exponential of the number operator of C.
By the way, did you check that your transformation?
Yeah.
Then probably your transformation has a problem.
No, it's not problem. It's just not usual. I will explain. So I understand that many people can doubt, but I think that you have to clear. So that transformation is also okay. We also doubt a lot. So we can check a lot. And so here you can introduce this J operator. And originally this Leclerc and his collaborator introduced it, and actually they resolve it. So this is really based on his work. So this is it's nothing but very similar to this -1 to the F in the Suji, but only C. So it's a unitary operator. At the same time, it's a Hermitian, and it flipped only sign of C, and it's a so-called the anti-commutate with commute with the B, and then they propose J inner product, so that you define new inner product by inserting J. Here, this is more like a supersymmetry, like a -1 to the kind of F or minus. It's insertion, you define new inner product. Then you can consider the J inner product, and then it turns out that it's positive definite. So for example, if you calculate this one, if you don't have this J, you will have this minus sign here, but this J flip the sign of the C oscillator, so you obtain the C -1 here, and then now the norm of the vacuum is the same as the excited state. So now it gives some positive definite norm.
Then why you take the vacuum as the usual norm only? Good morning. My brain is not working.
Of course, up to now, this is a fermionic theory. So bosonic, I can calculate this.
No, what I mean is that if you want to define, I guess, the inner product using J, then I think I would like to say that the vacuums inner product should be also defined using J.
Yeah, this is also J, and J is here. If you see here, J is invariant on if you act J on the vacuum, it's just same because number operator C dagger C.
No, it's J. You first have to act on the
vacuum. Then this is zero number operator. Then it's just one identity on the vacuum.
It's invariant.
Yeah. So
okay,
but you maybe I still doubt about it. So I also doubt because you say this is ad hoc, which means that you maybe trying to in order to resolve this kind of negative norm problem, you maybe is some artificially introduce this kind of artificial ad hoc to modify the modification of the theory to save the theory. So you might doubt it. I also agree. But well, in that paper, we show that this J norm, not the ordinary norm, follow from the path integral formalization.
Junggi,
Yes?
what is J square? Is J square minus 1 or plus 1?
A plus 1. Here, if you plus 1.
Oh, okay. So J square does not change the commutation rule for C, but they just seems to be curing the the major issue. Okay.
Yes.
Okay, I understood. Thank you.
So now we have to really start from the basic. What we learn when we learn the path integral, we start from this kind of transition amplitude, and insert this kind of completeness relation to each time slice, and then you connect the operator formalism to the path integral formalism. Actually, from the operator formalism, you get this path integral formalism. However, here the difference is that this couplingness relation. Here, I will not give the detail, but you can see this our paper, or you can also believe me. So that because here, for the couplingness relation, you need a minus sign here. So that that means, in other words, you can also insert the J here in the bra state. So the J equivalent. And because in this completeness relation, you have J operator on the bra, you can also insert here J because its vacuum is invariant. So because of this J, you can show that, for example, at the finite temperature, this trace of this operator formalism is the same as the path integral formalism. So this is why it's the same. You can also show like a non-zero, like a usual real time or whatever. So this is indeed, this J norm is really coming from the path integral. It's not just chosen by hand. So if you choose if you're using the ordinary norm, that is a wrong way to deal with this theory.
So what happens to sign
here? Why you need a minus sign here?
No.
Here? Because when J acts on the bra, sorry, I made a mistake. Here, 1 is 0. So I trying to explain. Yeah, this is vacuum. So that is the first thing. Yeah, sorry about that. This is typo.
Okay.
Yeah. So it's not at all. It's indeed some important thing. So if you define your theory, this model by Lagrangian, then correct operator formalism of this model should be using the J norm, not the original norm. So this is not the choice, but it's the correct norm. Actually, there are 2 ways to get the energy spectrum. One is that also you can using the Fock state here.
I'm sorry. So do you mean that any path integral need J?
No, particularly in this case.
So just again, my brain is not working. So tell me why, you need to insert in this case, only in this case you need to.
Because of this, I will show some detail later, the proof, so that the important part is this one.
Okay.
Here in completeness, because you insert the completeness in each time slice, and then this J should be up here. So somehow, yeah, you can show the just follow.
So first, then what is the origin of this sign here? Minus sign in the first line?
Because sorry, this is 0.
Right.
But if you act on this 1 on this first excite state, this one, like a C dagger 0, then you get also C dagger 0, right? In order to get it, as you see here, if you don't have a J, then it gives the minus C dagger 0, right?
Okay.
Yeah. So now, when you diagonalize this matrix, we first find the metric representation of Fock space representation of the Hamiltonian, not the usual ordinary inner product, but with J. J inner product. Then you can diagonalize it. This is similar to the bi-orthogonal basis when people study this non-Hermitian Hamiltonian. And or you can say you can study this kind of this diagonalization of this operator directly. So what I mean is that you consider some linear combination of state of the Fock space, and then you can find this eigenstate, not in the matrix, but in the operator way. Then you can find that the result of the Lisa is correct. Lisa calculate the energy spectrum from the just purely path integral. Just it's quadratic. You can easily integrate this path integral. So these two methods give this energy spectrum and consistent with Lagrangian. However, something is strange. This energy could be complex for this value within square root. Something is strange because previously you've seen that the Hamiltonian looks like a Hermitian. However, this is the problem. This is the key. So we define the new J inner product. So let's recall the linear algebra course when we learned this undergrad school. We usually learned the linear algebra a long time ago, but so there we define the J this adjoint or Hermitian adjoint, and that usually come from the inner product. So because we define the new J inner product, you have to also define new J Hermitian conjugate, so that this operate when you go to the act on this graph, it gives this. This is the definition of the J Hermitian adjoint, and then you can easily see that this new adjoint should have this J to get this relation. Then, when you talk about the hermiticity of the operator, you should using this J Hermitian adjoint. So that means this operator O is J Hermitian means that this one. Now, let me ask again, whether this Hamiltonian is J Hermitian or not. Yes, this is still Hermitian. This is still J Hermitian because it's a quadratic in C, so it does not change sign. But here, this term change the sign because of it's a Hermitian in the usual sense. But because when J acts on here, it flips the sign of C, so that it's not Hermitian because of this one. And then, since Hamiltonian is not J Hermitian, it is not surprising to have complex energy, so that you have this kind of complex energy. And you can realize, you can also see that a special value of theta, for special value of theta, this you can show that, you can also see that this one, the Hamiltonian become the Hermitian, explicit Hermitian. So this special value just means that this one is zero, so that this appear, you obtain this one. And you can easily see that this agree with the original spectrum. And then you can see that the solution of this equation does not exist always, which means that, let me plot this right-hand side in here, this curve. And the hyperbolic tangent defined only within the -1, plus and the -1. So only this part, only this range of the m lambda, you can define this kind of a special value. So that this is this kind of a range, this one. Only when, it's opposite, sorry. It's opposite. So there are many types because I prepared it yesterday. And as you see here, this is identical to the condition for the real energy spectrum. So lesson is that, so here Hamiltonian looks like a Hermitian, but because of this J inner product, which come from the path integral formalism, new J inner product, you have to define the new J Hermitian. And in principle, it should not have real energies eigenvalue. But if there exists some group of transformation where under which the Hermitian become the J Hermitian, then you can recover the unitarity. Because this is a quadratic theory, so that I think real energy is enough to say that it's unitarity. Sorry, it's over time.
Yeah. So could you wrap up in 5 minutes?
Yeah.
Just the most important part, please.
Yeah. So symplectic fermion. So this is some new work with the Shinsei Ryu, and I hope it appear in the next week, hopefully. And historically, it appeared a long time ago, as you see here, the first time, and they also trying to connect to the ghost, as you expect. I will show this model, and this also appear again in the context of the higher spin BSCFT. And then, as you see here, that's what I studied a long time ago because of, as you see here, paper, my advisor, and at that time I was also group, so that's why I know this model a lot. And but I don't claim that BSCFT in this one. I just claim that talk about this purely theoretical perspective, and this is model. So you can just consider it as this anti-committing scalar. It's almost scalar field, but it's just a Grassmannian, like a course. So I only consider the NS sector, and you consider the mode expansion. I just the most part is just parallel to the. So that's why I talk about the quantum mechanics, so that I remove the unnecessary part, and the mode expansion you also obtain this minus sign in this another operator. And then key part, it's the same story. You have this anti-commutation relation, give the negative norm, and this you can cure the theory, and you also have to define the J norm, J-Hermitian adjoint, and you have a positive norm and the real energy eigenvalue, and you can say that it's unitarity. Actually, this is already working with this layer a lot. However, now you can calculate the central charge. For example, you can using the OP, then you can also see read of the central charge, and you can also calculate the velocity generator, and you can find also negative -2. And there is a well-known proposition. CFT2 has negative central charge, should have a negative norm state. That is what we know. There is a big tension between these two. It's a negative central charge, -2, but it's positive norm, as I said. This is not the ad hoc, but if you calculate the path integral, you can show that you have to using the J norm, and it's positive definitely. What's wrong with that? So usually, let's recall this original proof for this proposition. So you will calculate this norm of this state, and using the velocity algebra, you obtain this one. And when C is negative, then for sufficiently large n, you have a negative norm. It's just quick proof. But here, the loophole is the J norm. So J-Hermitian adjoint of Ln is not the L-1. You can also show that because this you can see that. This usually there is a linear term in C. So this one BB and CC is okay, but the BC has a problem. So when you take this J norm of this state, then you obtain this one. Not here originally there is no J here, but here insertion of J. So you cannot use the velocity the algebra in this one, and then it's kind of loophole of the original stuff. So the upshot is this is unitary CFT2 with negative central charge, and you can also worry about this entanglement entropy, because now we know that the entanglement entropy is proportional to C, and when C is negative, then this definition using the reduced density matrix, it should be positive, because if you have a unitary theory, this definition with the law should be positive, but the right-hand side is negative. It's something strange, but it's not strange because you have to using the effective central charge. This series of papers show that when you calculate entanglement entropy, you have to using the effective central charge, which is defined by C minus 24 of the vacuum, the conformality measure of vacuum. So now in this case, it's just 1, so that is positive. But the reverse is not true. So what do you mean? Not this is, but you cannot say that positive effective central charge is unitary because this is Liang model is also central charge is negative, but the effective central charge is negative, but the effective central charge is positive. But we say we know that Liang is non-unitary. So
here in this
no, it's Grassmannian. Oh, so fermion. So that's the which one? Liang model or this one?
Oh,
fermion. And so there is a similarity to, we also find a similarity to the quantum field theory in the digital space, but I don't claim that, we don't claim that this is digital shape, but we found some similarity, and I will show some detail in the paper in the future. Yeah, thank you very much for attention.
Okay, let's thank Junggi for an interesting talk. Is there any urgent question?
I have a question. So you mentioned the relation.
Sorry, excuse me. Could you use a microphone? We cannot hear online.
Okay, you mentioned the relation between the negative central charge and unitarity issue in the 1+1 dimensional conformal field theory. But if you know the real gravity theory, for example, the stellar gravity theory, which includes the post-order gravity theory, so we could not achieve the denormalizability without the violation of the unitarity, actually. So many people are focused on this issue, but still we have a stayed unsolved problem. So in the case, we could not obtain the corresponding CFT theory. So then how to resolve that issue in terms of your model?
So, you mean it's kind of holography or?
No.
Just in the gravity side.
There is no such holography in the high order gravity theory, the Minkowski
just
space.
A pure gravity side.
Yeah.
So it's very interesting, but the problem is interacting theory. Here, we can get that conclusion because it's quadratic free theory. Interacting, it would be highly difficult, but I hope that there is a way to also attack this kind of some resolution in the interacting theory. But for now, I have no concrete analysis for that. But
so in this sense, you are studying the toy model in the 1+1 dimensional theory.
Yes, toy model, and in the large N theory, there is a nice like a proposal to the holography, but of course many people will not agree. But I mean, just historically there was some proposal.
So is there any case in the for bosonic negative C case? I mean, by introducing some chain, or you can cure the problem also.
Maybe there is some. For example, one is this the Ostrowski instability problem has. Usually it's known that it has a negative norm, but a very special case, people found that it's well defined without using the J norm, but using some measure. So some case, yes, but I'm not sure all the case.
So any other question?
Sorry, if we consider the a bosonic series like a PT symmetry, but non-Hermitian. The potential is I lambda 5 to 3 turn like that. So do you mean that Lagrange passenger formulation should be changed?
I don't know. It depends on model. You have to check.
Okay.
It's not. I'm not saying the universal one. I just saying that some counter example.
Okay.
That doesn't mean that I can solve every problem. Of course, there is an inherent. I mean, the non-unitarity. Most problem you cannot avoid. Well, but I'm just give the one counter example. That's all. You can.
All the Yang-Mills ghost as a negative norm, right?
Yeah.
And then in that case also you can convert those ghosts to something normal.
I don't think so. Because I mean, if you change the model, maybe, but it also make another problem. So what I mean is, as you say, you can define some kind of norm. I'm not sure interacting case, but to cure this model, but it would not consistent with the original path integral.
What I would expect that would be disaster, right?
Yeah, that's right. That's right.
So that's why I mean the possibility of the negative norm fermions into the positive norm state is a little bit suspicious.
Usual case, yes, but in this case, it's opposite. This new norm is correct. The original norm is incorrect. From the point of path integral, you just diagonalize the path integral, then you obtain that.
Yeah, I understand what you did, but let's see.
Okay, so I think we should stop here. Let's thank Junggi again for a very interesting talk, and let's continue.